For the next example that I want to talk about, we're going to have to talk about some preliminary things first, in particular, a procedure called quantum state discrimination. And I'm going to talk about a particular form of it called unambiguous discrimination. Now, quantum state discrimination is the following problem. You have Alice, and she sends a qubit, which is either in the state psi 0 or psi 1 to Bob. And Bob knows what psi 0 and psi 1 are, but he doesn't know whether the qubit that Alice sent him is in psi 0 or psi 1. So he has to perform a measurement to try to figure out whether he got psi 1. So he's going to measure. Now, if psi 0 and psi 1 are not orthogonal, Bob can't do this perfectly. So there are generally two different strategies for the kind of measurement Bob should make. The first one is called minimum error state discrimination. So Bob's going to measure, and every time he gets a qubit from Alice, he's going to give an answer. So he's going to either have to say psi 0 or psi 1. But because psi 0 and psi 1 are not orthogonal, that means that some of the times he's going to get it wrong. And the minimum error strategy is a strategy that for Bob's measurement, for which he will make the minimum error. So in other words, he'll be wrong the smallest number of times. So that's one strategy. Now, unambiguous discrimination is a different one. In unambiguous discrimination, Bob does a measurement, but he never does an error, never makes an error. So what happens? So the unambiguous case is that Bob makes a measurement. He gets one of three results. He can either get 0, which tells him that the state was psi 0. He can get 1, which tells him that the state was psi 1. And he can get a third result, which I'm going to call F for fail. So in this measurement, it never makes a mistake. But can fail. And it lets you know when it fails. So in other words, you put the qubit into an unambiguous discrimination machine, and it spits out one of these three things. It either tells you 0, which definitely means it's psi 0. It is 1, it definitely means it's psi 1, or it spits out an F, which says, sorry, the measurement failed. I can't tell you anything. And the idea, in most cases, is to try to minimize the failure probability. But it turns out, in what we're going to be doing, that's not necessarily what you want to do. Okay, so I'm going to discuss a particularly simple example of unambiguous state discrimination. It's not the way to get the best measurement, but it's just to sort of give you the idea of how this works. All right, so we're going to look at a very simple version of unambiguous state discrimination. So what's Bob going to do? So this is a very simple version. And this is not the best. Okay, so what's going to happen here is Bob is going to measure he's going to get his qubit from Alice, and he's going to measure in the psi 0 per basis. So Bob measures. So let's see what that looks like in a picture. So I'm going to have, so this will be 1, and this will be 0. And let's suppose things look sort of like this. So here's psi 0. And here's psi 1. So they're not perpendicular to each other. So Bob is now measuring in the psi0, psi0 perp basis. So let me put in psi0 perp. Psi0 perp is the vector that is perpendicular to psi0. It's supposed to be in, right? So when he does his measurement, he's going to get one of two results. He's either going to get psi0 or he's going to get psi0 perp. So what happens if he gets psi0? So, okay, so he can either, as he said, he can either get psi0. So suppose he gets psi0, what can he conclude? Basically not much, because the point is that both psi1 and psi0, clearly psi0 has overlap with psi0, but so does psi1 because they're not orthogonal. So this would be a fail, okay? Because this gives me no information. Both psi0 and psi1 have overlap with psi0. Okay, then that's what he got. So that corresponds to a fail if he gets psi0. So what if he gets psi0 perp? Well, hopefully that won't be a fail. So the only way he can get psi0 is psi0 perp is if psi1 was set, because psi0 has no overlap with psi0 perp. So this would imply that okay, so this is kind of a primitive unambiguous state discrimination measurement. Now we have the figure for the states that we're considering here. So 1 and 0 are just those are the states on the computational basis. Those are perpendicular to each other. Psi0 and psi0 perp are perpendicular. So the overlap between psi0 perp and psi0, it's 0 because the angle between them is 90 degrees. Now psi0 and psi1 are not perpendicular to each other. So let's call this angle here theta. So what's the overlap between psi0 and psi1? So let's let S equal overlap. And that's simply going to be equal to cosine theta. Now, when Bob does measurements, he's measuring in the psi0 and psi0 perp basis. So he's either going to get psi0 or psi0 perp. So suppose he gets psi0. Bob gets. So what can he conclude? And in this case, the conclusion should reflect the fact that he does not want to make a mistake. And in this case, he really can't conclude anything because, so if he gets psi0, obviously psi0 has an overlap with itself of 1, all right, because it's the same vector. But psi0 also has an overlap of S, which is not 0, with psi1. So there's a certain probability that if psi1 is sent, that Bob could measure psi0. So with either psi0 or psi1 sent, he could in fact get the result psi0. So that means that this is a fail because both psi0 and psi1 Now let's see what happens if he gets psi0 perp. Now he can only get psi0 perp in one way. Because psi0 perp and psi0 have an angle of 90 degrees between them, the overlap between those two is simply 0. Cosine of pi over 2 is 0. So there is no overlap between size0 perp and size0. That means that if he gets size0 perp, he can conclude that psi1 must have been sent. It can't have been size0 because size0 can't produce a result of size0 perp. So in this case, what he can conclude is that psi1 was sent. So this particular scheme, it is a version of unambiguous discrimination. It's one that only detects psi1. It'll never detect psi0. Because if psi0 is sent, we get an automatic fail. So, but it will detect unambiguously psi1. If psi1 is sent and Bob gets psi0 perp, that means that he can tell from that it was psi1 that was sent. Now, what we're going to do is now we're going to go take a look at the more sophisticated version up here. And I'm just going to tell you about the results of that. I'm not going to go through the details because it's a fair amount of calculation and things like that, and which we really don't need to kind of understand this measuring twice business.